Hi, I'm Sarah Gutterman. I'm CEO of Green Builder Media, and I am here today with Hakan Yilmaz, the president for Carrier Energy and the chief sustainability officer for Carrier. Can you please tell me about Carrier's field trial of your heat pump HVAC systems with battery backup that fits into this whole concept of distributed energy resources?
We are redesigning, redefining HVAC and how it operates in a more grid-friendly, grid-resilient way. It's really a turning point for the whole industry. We are right now piloting a next-generation residential HVAC system that integrates variable speed heat pumps with battery storage. These systems are designed to shift energy use away from the peak periods, improving the grid responsiveness while maintaining the homeowner comfort, which is super important for us. The goal of the field trials is to validate the system's ability to reduce peak electricity demand, enable demand response, and support the grid resilience, which we all need right now to deliver the load coming from AI demand and also from electrification needs. We are collaborating with Electric Power Research Institute, EPRI, to provide our third-party validation of the field trial. And EPRI is conducting instrumentation and utility-grade assessments to ensure that credible results that can inform regulatory filings and utility program designs.
Do you have any specific goals relative to peak load shifting, peak load shedding? And then how does all of that translate into benefits for homeowners as well as for utilities?
We as Carrier are fundamentally reimagining how the HVAC systems operate and how they become active participants in the grid management rather than staying as passive energy consumers. And as you know, HVAC load on the grid is really massive. About 40% of the peak capacity in the US grid is dedicated for HVAC load. And this core innovation, which is really homegrown organically with our teams, involves integrating onboard dedicated batteries to the HVAC units. Homeowners with this solution maintain full comfort. No behavioral changes required. If they want to have 72 Fahrenheit flat in their home, they get their 72 Fahrenheit flat in their home with the perfect comfort and no sacrifice. The system operates as usual, but it avoids drawing power during high cost peak hours, potentially lowering energy bills and improving cold weather performance with battery assisted heat pumps. Utilities gain access to millions of distributed dispatchable assets that respond in real time to grid conditions, and this supports, in return, renewable integration, enhances reliability, reduces the need for costly infrastructure built solely to handle HVAC-driven peaks. So we're turning very predictable but uncontrollable HVAC peak load on the grid to a very controllable asset for the grid.
Let me ask about the installation, Hakan, because obviously this will be, battery backup storage is not a typical installation use case for HVAC contractors. So, are you training your HVAC contractors to install the battery backup system as well? Is it integrated? Is it an easy install? Or do builders need to bring in an additional contractor to then install that battery backup system?
First of all, we have a very strong installation channel in the US. We are pretty much 1/3 of the US market on the residential side, and we have very strong distribution and channel partners. And we are designing the battery installation and integration in a simplified way. So it is very quick, it is very scalable, it is very manageable in terms of installation and maintenance so that our technicians can handle it very easily.
Have you designed this HVAC and battery backup system to address resiliency? You've talked about peak load shifting and peak load shedding, but can you talk a little bit about maintaining the independence of a home during, say, a grid outage?
We are really addressing the actual root cause of these congestion problems. Our system addresses the concerns and flexibility needs of the grid by flattening the demand curves and easing the stress on the grid during extreme weather or high usage events. So since when the grid is under stress, like extreme weather or high demand, it's more likely going to experience outages, our solution delivers a flexibility. That means the grid can operate during disruptions by reducing the peak demand, supporting recovery by means of delivering distributed energy. So we are really doubling down on the root cause that causes the situation, on the stress on the grid, and eliminating that. So if you don't have a peak coming from the HVAC, the job of the utilities become a lot easier.
As you mentioned, you're working with several utilities on this field trial. Now, what have those collaborations revealed about scaling demand response and load flexibility? And have you had any conversations with the utilities to date about offering any kind of rebates or incentives at a utility level for this type of a system that can really help eliminate that grid stress?
The way we work with utilities is all about scaled expansion of these solutions. If you look at our partnerships with utilities, they're all trying to solve the congestion problem, right? There is the HVAC load. HVAC load is on majority of the built environment in the US. And then there's the electrification coming up. The energy prices are going up. What we do is we are flattening the load of the HVAC. We are removing all the congestion coming from the HVAC load, giving the relief back to the grid, and it creates a lot of value for the grid. Because a lot of the inefficiencies and the cost of the grid comes from the peak load, right? Majority of the expenses on the grid side from distribution peak, which is around 3 to 4 p.m. in the afternoon, pretty much caused by the HVAC load. It's the hottest time of the day. And then you have the system peak, which is about 6 to 8 p.m. when the sun is down, the solar is gone, and you're relying on peakers, and people are still at home and they have this air conditioning running maybe at 70-80% load. We relieve that congestion as well, and we help avoid peaker plants. Plus, there is additional load coming from data centers and other industrial load and EV charging that start on schedule around 10 p.m. By removing the load of the HVAC from the peak, we enable the existing capacity on the grid to be used for these other electrical loads. All in all, what we do is we create efficiency and better capital utilization of our existing grid. And of course, when you increase the utilization of the existing grid, the costs come down. And what we're looking for is a solution that unlocks value for the grid, it unlocks value for us, and it shields the homeowners from discomfort, price hikes, and also reduction in their energy bills because they avoid using electricity for their HVAC during the peak hours where energy generation is the most expensive. Because they can use the energy that they stored around noontime, which is a lot cheaper.
Does your system currently connect to other demand-side energy management systems like solar, even whole home battery backup systems, EV chargers, and other smart devices to create a comprehensive demand-side energy management whole home system?
All of our connected units, all of our batteries come out of the box connected either to Wi-Fi or cellular network. That connectivity enables us to talk to any other appliance in the home or the grid, to the substation, the grid operator. However, our current battery-enabled system is designed to be a grid interactive standalone solution that prioritizes ease of installation, cost effectiveness, and utility program compatibility. We are invisibly scalable, and that's our priority. The initial product launch deliberately avoids these connections for several reasons. They will come later, it's possible, but we want to reduce complexity and upfront costs. The fact that the battery is only connected to the heat pump avoids additional setup and assists with the overall adoption. Back to your question about how do we train the technicians, we want to make our technicians and installers' life very easy, and we want to have this process seamless and invisible to the homeowner, so it can be scaled in a hassle-free way for our installers and for the homeowners. And since there is no interconnection required to your panel or anything, and everything happens behind our outdoor units connectivity, the system is very fast to install, provide fast access to be optimized for demand response programs. And this is how we would like to come to the market. And of course, we are thinking about other ecosystem partnerships, talking to other behind the meter assets like smart panels and EV chargers and solar panels and inverters and other things. But that will come at a second stage after we are installing our batteries and making them work for the grid. That comes as a bonus later.
We are seeing a rapid expansion of virtual power plants or VPPs. So, does your system or will it at some point play a role in VPPs?
By turning our install base of residential HVAC systems into dispatchable grid interactive energy assets, Carrier can play a central and transformative role in VPPs, especially with our scale of load and controllability. The battery-enabled HVAC systems installed across thousands or even millions of homes can be aggregated into VPPs, allowing the utilities or aggregators to control fleets of HVAC systems. Think of it as a macro grid of HVAC systems talking to each other in a unified way.
I'm curious to hear what kind of performance variability are you seeing in your field trial across climate zones and regions?
There's a variety, right? We are attaching our HVAC and battery together to operate as one unified product. And we are seeing different type of requirements on each utility ecosystem. First of all, our utilities, and we have over 2,000 of them, are like snowflakes. They are all in different climate zones. They all have different regulation. They all have different customer requirements and customer base. They learn from each other. They adopt the new solutions fast if it really works for their KPIs. But at the end of the day, each utility has a different requirements. Some require a day-ahead demand response. Some require in 5 to 10 second demand response. Some require a full aggregation. Some require an upfront programming and different type of connectivity requirements. So we are working with each utility partner we have and solving their real problems as a partner. And the way that we are approaching this problem is HVAC is very climate dependent product, right? It's climatization. It's basically control the temperature in your house. We have 4 different sizes of HVAC, 2 ton, 3 ton, 4 ton, 5 ton, different type of tiered products, and we operate in different climate zones. And of course, if you're operating this HVAC unit in Texas, hot and humid, like in Florida where I am right now, it's going to act very differently in terms of grid interactivity compared to, let's say, New York or Midwest. Because of that climate and temperature dependence and how you build a home, the size of the home, it's a thermal management device. It's very custom solution based on the location, based on the size of the building, size of the HVAC, size of the battery, duration of the demand response, and the maturity of the VPP programs of the utilities. Sound complex, but it's actually possible. And we're working with all of our utility partners through our advisory committee who's overseeing our test results. And we're making sure that in collaboration with multiple utilities, we consider all of these options and requirements and make sure that we have a solution that's nationwide scalable with all of the utilities that we work with.